Yeah, so this is a talk about this archive. Sorry, this archive paper. Our trio is famous for this paper, quantum batteries, where we proved some conjecture um, about charging. But I'll talk about this. So um, the overarching question here is. How fast can we charge with quantum battery? I'll start with the outline. As others said, I will overlap a lot with especially the morning session here. So I'll talk about quantum batteries, and then I introduce the main results, how to compute it, and talk about some takeaways. So what is a battery? A mountain dam is a battery. Charging battery means that we take a state that has no energy and we charge the battery, for example, by bringing water into a dam from the valley. This is another example. And quantum batteries, as many said, is that a somewhat different beast from classical ones. So in classical, you have some discharge state and some charge state, which here I will model as like spin up and spin down. But in quantum, you can have anything in between, which is a different thing. So you can have a state, and this first qubit corresponds to a single cell potentially, and the second one is a second cell. So you can have 2 spins up or 2 spins down, and some superposition. So you already knew that, right? So let's move to the main topic. So at the quantum level, the 2 qubits form a new entity. We have entangled states. And I'll specifically talk about these shortcuts to charging. So when you have a quantum charger, it charges all the spins at the same time. There is some kind of charging of all of them at the same time, and then you create this charge state. While classically, what's usually considered is that you either charge all of them separately, independently, but with less power, or one at a time with more power. So this is what I try to like shown here, is that this is what other people here called fair comparison. So either you have a charge that charges all of them at the same time, or you have the same power but charging one at a time, and this is the classical. And one feature is that quantum physics allows entangled states, which actually expands the states that you can go through, and this creates some sort of shortcuts. So classically, you can think about charging as just going onto these paths, which are just perfect classical. There's no entanglement. So you take this one, you charge it, and then you charge the second one, and you get to the charge state. But somehow you can exploit the structure of Hilbert space and go through something that's not classically possible. And this is the quantum charging. So the big question is, what is the minimal time it takes to charge a quantum battery? What one has to do to achieve that? Now, a bit of math. We consider 2 quantum states which have the same spectra, because we will consider unitary evolutions. So that's one of the assumptions here, which will be key, and I'll get back to it later. We consider only unitary evolutions. And we can take a depleted state or uncharged state and charge it with some unitary. Therefore, our charge state will be unitary transformation of the depleted. And now to consider the minimal time it takes to charge a quantum battery, we really need to define it. So we assume we have some charging Hamiltonian, or you can call it driving Hamiltonian, V. So this is the charge state. And the unitary here is time-ordered exponential, and this would be normal exponential if this is time independent, but we want to make it as general as possible. And we simply define the charging distance as the minimal time it takes to charge a quantum system. So it's the minimum over all of these times, and where you optimize over these charging Hamiltonians. With this condition, that's very common in quantum batteries literature, on the operator norm equal to 1. So you can think of this operator norm as some kind of voltage, because if you take this one and if this is not equal to 1 but equal to 2, then you can charge twice as fast. So this is the notion of equal footing. So we can set it to 1, and then if it is some other number, we know we just multiply or actually divide the time it takes to charge by that number. And notice this is optimizing over charging Hamiltonians. And again, this is unitary evolution. So let's recap. We have the unitary evolution, time exponential, and then we have this definition. It is a distance. It has these 3 properties of a distance. But the question is really how to compute it. It is not really that easy to see how to derive something like that. But we managed to do that. We can compute the charging distance as the minimum over some minimization procedure. And now you can see there is no time anymore. There is only these unitaries. So we now minimize over all the unitaries that transform the depleted state into charge state. You take the logarithm of this unitary and take the norm. This is still pretty difficult. However, for pure states, the optimal Hamiltonian can be computed. Actually, no, this is for all states. The optimal Hamiltonian can be computed as like this. It still doesn't give an exact prescription how to compute it because the optimization is not that easy to do. But for pure states, we actually derive the formula for it, and it's equal to the Beres distance, not the Beres angle. What you notice here that this actually depends only on the overlap, and with any charging system, your depleted states is like, let's say, all zeros, and your charge states is all ones. But this depends only on the overlap, but the depleted and charge states are always orthogonal. So this distance will be always equal to pi half, no matter how big system you have. For pure states, for mixed states, it's more complicated, and it still reduces to minimization problem, but it's somewhat tractable. You need to minimize over some phases, and these SI are eigenvectors of the charge state, and this Ri are eigenvectors of this charge state. And you just need to map these 2 bases onto each other and then optimize over these phases. The key takeaway of this distance is that actually does not depend on the eigenvalues explicitly. It depends only on the eigenspaces. And interestingly is that it depends on the eigenvalues only discontinuously. It's only when one of those subspaces become degenerate, then the charging distance jumps. We have some bounds. So for pure states, it is equal to this, the charging distance equal to the Beres angle, which is smaller than pi half. And for mixed states, it's actually bounded by pi, and it's bigger than Beres angle. And I can visually say here that, okay, if you have this charging distance, it's evolution of some Hilbert space, and then you have some classical charging that doesn't create entanglement, and the Beres angle is somewhat even faster than the charging distance. Yeah, so this is the outcome basically for pure states. We know that for classical charging reaches the charging in pi, and for quantum charging is pi half. But this increases with n, and this doesn't. So that's the key takeaway. If you have classical charging from 0 to 1 takes pi half for classical charging, but if you have n cells, it takes n times that. But for quantum charging, it takes the same time. However, for quantum charging, in order to charge the fastest possible, you actually need to go through the GHZ state. And this is a significant technological challenge. Also because the GHZ state is highly sensitive to decoherence, because while charging, if one of those charge states get depleted, all of them get depleted because it's perfectly correlated state. And then brings us to the next slide, key takeaways. So to achieve n-fold advantage, one is to entangle n qubit at once, and this is for that you need extremely high entangling operations. And in that aspect, it's actually more difficult than quantum computing. And that's because in quantum computing, you just need 2 qubit operations to create anything you want. But if you use 2-qubit operations here, yes, you can create GAZ state, but it's not going to be fast. And also this GAZ state is highly susceptible, so decoherence, so we need perfect isolation when charging. When it's charged, it's no longer a problem. However, we can take a progressive approach. For example, if you have 2-qubit operations, we achieve 2-fold advantage. And that's possible. And if you have 3-qubit, you can take 3-fold advantage. There might be another way how to do this, and that's probably related to more this Dickey model. And that's, if you remember the assumptions here, I considered only unitary evolutions. But maybe you can charge by non-unitary evolutions, and that's exactly related to this Beres distance. So the Beres distance corresponds to the charging distance, but in the extended space. And in the Dickey model, you have some external field as well. That's not the battery, the light field. So that can maybe give you a bigger advantage. But if you consider just unitary evolutions, then these are the bounds. And some extra things to consider. The definition of minimal charging depends on the operator norm. If you remember, we had some condition that the operator norm is equal to 1, but there is no particular reason why we should choose this norm. We can take some other norms, and it's not really quite clear which norms are experimentally more sensible. That should be discussed. And also, given these different norms, we can have other minimal times, because depending on the norm, we can have different geodesics on the Hilbert space. And finally, no state is really pure. So for mixed states, the charging distance depends on the lowest eigenvector, because we need to map every basis vector to every other basis vector. However, some slowest eigenvectors might not carry much energy. So maybe there is some kind of trade-off between charging time and maximal capacity of the battery. Maybe we can charge more faster by ignoring certain subspaces. But that limits the maximal capacity, and that's somewhat analogous to standard batteries as well. That it takes much slower to charge the last 20% of the battery than the rest 80%. And that leads me to a conclusion. We defined the quantum charging distance, derived its formulas for pure and mixed states, found that it quantifies the quantum charging advantage geometrically. And we discussed experimental challenges and needs for future investigation. Thank you.
Questions? Oh, one at the back first.
Thanks. Thanks for the talk. I wanted to ask you, how is it related to the speed limits that Kevin talked about this morning?
I don't know about this morning, but you can derive speed limits from this definition, which is exactly like, always perfect. Because we actually computed what is the minimal time, so it's not speed limit, it's computed. It is equal, it's like the lowest bound. The trouble with this quantum charging distance is that while it's easy to compute for pure states, it's difficult to compute for mixed states because it leads to optimization procedures. And for pure states, the speed limits, all the speed limits that have been derived for pure states, they are kind of coinciding. But for mixed states, this is actually the best you can do. So there's no limit. But the good thing about quantum speed limits is that they are usually easier to compute than the actual speed. And that's also true here. So we actually derive formula for the actual fastest speed that you can achieve, but it's not easy to be computed.
So if I understood correctly, you didn't have any constraint on the type of unitaries or Hamiltonians they were using to generate these evolutions. And I saw that you guys presented a approach to get, like a proactive approach to get those trajectories. So I was wondering if you're trying to extend this to cases where you actually have limited control instead of just any Hamiltonian to generate the evolution. So in other words, that maybe you cannot use any Hamiltonian to charge your system, but you only can use Hamiltonians with some particular combination of Pauli operators and so on and so forth. So you have
Right.
restrictions.
So we consider restrictions only on like classical charging. So there you can derive a different distance, the classical charging distance, which where you restrict the Hamiltonians on those that do not create any entanglement between subsystems. Yes. So there actually I showed these results. It was n times slower than the quantum. And you can consider also some other, other limits, but we just took the perfect case. And we know that, for example, for pure states, to achieve the fastest charging, you always need to go through GHZ state. So entanglement operations are necessary.
Thank you.
Any further questions? Yes.
Thank you very much for the very clear talk. You first assume that we apply unitary operators and then you relax this constraint, and you also mentioned that you can use different norms for the potential V that would give you different distances in the Hilbert space, and different minima, different geodesics. And one thing that you didn't relax is the assumption that the initial and final density states should have the same spectra. But physically thinking, one can always tune some parameters in the Hamiltonian, and in the charging state, the Hamiltonian might be slightly different than in the discharge state. Or one can periodically drive the system or do something so that the energy levels are allowed to change. So can you account for this possibility within the framework of this proof?
Okay, so within the framework, no, because we assumed only unitary evolutions. So unitary evolutions cannot change the spectra by definition, right? So, but you can charge maybe by some master equation, but then you need to do like different definition of charging. The trouble with non-unitary evolutions that if you introduce some non-unitary evolution and doesn't purify at the very end, you are really damaging your battery, right? If you have a mixed state and you don't get to the initial state that's pure again, then you are your capacity is getting lower. So I'm not really. I think what you will be extending this work will be to consider non-unitary evolutions that initial and final state have the same spectra, but in between can be different. And in that case, you can possibly use the other like extended Hilbert spaces to get faster charging, but doesn't degrade the capacity of the battery.
Let's thank all our speakers again.